This lesson is on Dalton's law of partial pressures, and this law is going to state that equal amounts of gases at the same temperature and volume all have equal pressure. And so what it's basically saying is the total pressure inside of a container is equal to the partial pressure of each gas. So basically you just add them up. So our formula for Dalton's law of partial pressure looks like this. P total, so that would be the total amount of pressure, is equal to the partial pressure of gas 1 plus gas 2 plus gas 3, etc. As many gases as you had. Okay, so it's a pretty straightforward law. Where it comes in, gets a little bit confusing is when we do the collection of water over a gas, which we'll talk about in a second. So very quickly, this is going to be a fast lesson. Here's an example. If we had this container over here, this final container over here is adding these up. So we'll call this 1, 2, and 3 containers. Okay, and basically, if we wanted to figure out how much the total pressure is in right here, so we'll call this total, we would take that equation and we would say P total is equal to P1 plus P2 plus P3, and then we would say that would be 2 plus 1 plus 3, and so my total pressure would actually be 6 atmosphere. I know it seems too easy, doesn't it? So here's a couple of examples. It says, what is the total pressure in a balloon filled with air if the pressure of the oxygen is 170 millimeters of mercury and the pressure of nitrogen is 620. So I literally would say P total is equal to 170 plus 620, and my answer would be 790 millimeters of mercury. And that would be my answer. Seems too easy, doesn't it? Okay, in the second balloon, the total pressure is 1.3 atmosphere. And so it wants to know what the pressure of oxygen is if nitrogen is 720. So what we would do there is we would say the pressure of oxygen is equal to P total minus the partial pressure of nitrogen. Okay, and so we would say that we'd have 1.3 atmosphere, and here we have, so we run into a little bit of a problem because we have to be in the same unit, okay? And so it's just your personal preference. It's just my habit to go to atmosphere. You could do it the other ways too. I just like to go to atmosphere. So I'm going to have to go over here and do a real quick conversion and say 720 millimeters of mercury divided by, the conversion factor is 760 millimeters of mercury is 1 atmosphere. And when I do that, I get 0.95 atmosphere. So now I can go plug this in and say 0.95 atmosphere, and then I get that my total my partial pressure of oxygen would be 0.35 atmosphere. Okay? Anytime you're doing any of these gas laws and you have units that don't match, you've got to make sure they match before you can use them. Okay? And like I said, it didn't matter if we went to millimeters of mercury or atmosphere, it's just your personal preference. I tend to go to atmosphere because when we get to the ideal gas law, we're going to put everything in atmosphere. So it's just a good habit to get into. So an application of Dalton's law, and we're going to be doing a lab over this, is collecting a gas over water. Okay, so basically, and there's a whole bunch of notes here that you can read through if you don't understand it, but basically when we collect gas over water, what happens is some of the gas that we end up collecting is water vapor. Okay, and water vapor has its own specific temperature. Okay, and so there is a whole table in your book, and you can look them up online, of water vapor pressures, okay? And they're dependent upon temperature. And so when we collect a water over gas, we have to account for that vapor pressure because it will actually have a little bit higher pressure than it should because it is collecting water vapor. And like I said, you can walk through those steps and kind of see what we're doing, but I'm just going to kind of show you. Okay, so let's see if we can do this pretty straightforward. This one says a gas collected over water at 8 degrees Celsius in a 350 milliliter vessel has a total pressure of 634. Okay, torr. And then it wants to know what is the volume of the dry gas at standard pressure and 8 degrees Celsius. Okay, at standard pressure and 8 degrees Celsius. So we have to figure out what that would be. Okay, and so the water vapor is going to be 8.1 torr at 8 degrees Celsius. Okay, and standard pressure, of course, is in torr is going to be 760 torr. Okay, so what we're actually going to need to do here is we're going to figure out the corrected pressure. Okay, so this is actually going to end up being our P2. Okay, and because it's asking for volume here, so we're going to be looking for V2, and we started with V1. So P2 is going to be standard pressure, so we actually have to go back and calculate what P1 is. And we're going to have to do that by subtracting our water vapor. So we're going to do P dry gas is what we're going to be looking for. So we're literally just going to take this 634 torr, and we are going to subtract out the 8.1 torr. Okay, and we would get 626 torr. Okay, so now that's going to be P dry, but it's also going to be known as our P1 because that's the initial pressure. So it wants to know what would it be at standard pressure. So we're going to be using, when we use pressure and volume, we're going to be using Boyle's law. So P1 V1 is equal to P2 V2. And this is what we're solving for. So V2 is going to look like this. P1 V1 over P2. So now let's go put in our P1, which was our corrected pressure of 626 torr, and our original volume of 353 milliliters. We're going to divide by P2, which was when we raised it to standard pressure, which is 760 torr. Cross out our torr. So now 626 times 353 divided by 760 gives us an answer, V2, of, when we round that to 3 sig figs, 291 milliliters. Okay. And then we can double check ourselves again because our pressure increased. Okay. So we expect, if our pressure increased, we expect our volume to go down. And it did, because our pressure increased from a total of 620 torr to 760. So our volume should definitely go down. Oops, sorry about that. And that is where this lesson is going to stop. So I gave you a nice, short, sweet one.